We saw that the differential equation ay double prime plus by prime plus cy equals 0 for constants a, b, and c has an associated characteristic equation ar squared plus br plus c equals 0, such that the solutions of the differential equation are y1 equal to e to the r1t and y2 e to the r2t, where the constants r1 and r2 are the solutions to the characteristic equation. This meant that we could find solutions to the differential equation by finding solutions to a quadratic polynomial equation. Further, we saw that if r1 is not equal to r2, we could in fact build a general solution with y equals c1 e to the r1t plus c2 e to the r2t. However, since the characteristic equation is a quadratic polynomial, there are three possibilities for the roots. The case above is when the characteristic polynomial has two distinct real roots. Another possibility is that the characteristic polynomial has two complex roots. And the final possibility is that the characteristic polynomial has one repeated real root. We will study these last two possibilities, starting with the complex case now. To understand the complex case, we will first need a theorem that says if y is equal to u of t plus I times v of t is a complex valued solution of a differential equation of the form y double prime plus p of ty prime plus q of ty equals 0, then u of t and v of t are both real valued solutions to this differential equation. I want to point out that there are two important aspects to this conclusion. One is that u and v are solutions, and two, that they're real valued. Even though y is a complex solution, it is written in a way so that the imaginary part is isolated as the coefficient of v of t, but u and v themselves are real. To prove this, we'll use that u of t plus I times v of t is a solution to the above differential equation. So we know that if we plug it into that equation, the equation will be true. That is, 0 is equal to the second derivative of our function, u of t plus I times v of t, plus p of t times the derivative of u of t plus I times v of t, plus q of t times our function u of t plus I times v of t. Now, using the linearity of the derivative and separating out the real and imaginary parts, we'll get u double prime of t plus p of t times u prime of t plus q of t times u of t plus I times the factor v double prime of t plus p of t times v prime of t plus q of t times v of t, where we have now separated the terms into the real and imaginary parts. And a complex number is 0 if and only if both the real and imaginary parts are 0. And since the complex valued function above equals 0, we can conclude that the real and imaginary parts are both 0. That is, u double prime of t plus p of t times u prime of t plus q of t times u of t is equal to 0, the real part equals 0, and v double prime of t plus p of t times v prime of t plus q of t times v of t is equal to 0 as well. But these two statements mean, by definition, that u and v are both solutions to the differential equation. So we can conclude that both the real and imaginary parts of the complex valued solution are solutions themselves. So, from a complex valued solution, we get two real valued solutions. And we have shown that since u of t and v of t are solutions, then any linear combination of them, y equal to c1u plus c2v, forms an infinite family of solutions. But is it the general solution? To answer that, we will have to check if the Wronskian w is equal to 0 or not. But before we do that, we need to have a better understanding of what the solutions u of t and v of t are. So let's suppose that the differential equation ay double prime plus by prime plus cy equals 0 has a characteristic equation that yields complex roots r1 and r2. That is, the solutions to ar squared plus br plus c equals 0 are complex. And since this is a real valued polynomial, the complex solutions must come in conjugate pairs, gamma plus or minus I times mu, where gamma and mu are real values. Taking r1 to be gamma plus I mu gives a complex solution to the differential equation, since r1 is a solution to the characteristic equation. More specifically, that solution is y equals e to the r1t, e to the gamma plus I times mu t, is a complex valued solution. And we just saw that if we can split y into its real and imaginary parts, then each will be a real valued solution to the differential equation. So the question becomes, how do we split y equal to e to the gamma plus I mu t into its real and imaginary parts? Because if we can do that, then we will have two solutions to our differential equation that we can then use to build our general solution. So let's come back to the question, how do we split y equal to e to the gamma plus I mu t into its real and imaginary parts? The first step is to use our rule of exponents to rewrite y as e to the gamma plus I mu t is equal to e to the gamma t plus e to the I times mu t. Writing it this way, since e to the gamma t is real, if we can split e to the I mu t into its real and imaginary parts, then we will have y split into its real and imaginary parts. To do this, we can use Euler's formula to write e to the I mu t as cosine mu t plus I times sine mu t. And this gives us that y equals e to the gamma t times e to the I mu t, which we can now rewrite as e to the gamma t times cosine mu t plus I times sine mu t, which, when we distribute e to the gamma t, is e to the gamma t times cosine mu t plus I times e to the gamma t times sine mu t. And thus, we've written y in its real and imaginary parts. Y equals e to the gamma t times cosine mu t, the real part, plus I times the imaginary part, e to the gamma t times sine mu t. I want to emphasize again that even though we call it the imaginary part of the solution, e to the gamma t times sine mu t is completely real. It just has an imaginary coefficient. So we can conclude that the functions y1 equal to e to the gamma t times cosine mu t and y2 equal to e to the gamma t times sine mu t are real valued solutions to the differential equation a times y double prime plus b times y prime plus c times y equals 0, where r equals gamma plus I mu is a complex solution to the characteristic equation associated to it, ar squared plus br plus c equals 0. And since we have these two real valued solutions to the differential equation, ay double prime plus by prime plus cy equals 0, and we have also seen that if y1 and y2 are solutions to a second order linear differential equation of the form y double prime plus p of t times y prime plus q of t times y equals 0, then the linear combinations y equals c1y1 plus c2y2 is a solution as well for any constant values c1 and c2. So combining these ideas, we can see that for any constant c1 and c2, y equals c1 e to the gamma t times cosine mu t plus c2 times e to the gamma t times sine mu t is a solution. And to conclude that this is the general solution, we need the Wronskian w to be non-zero. While we won't compute it here, if we compute the Wronskian w, we can show that w equals mu times e to the 2 gamma t. And since the exponential e to the 2 gamma t will never be 0, the only way for this product to be 0 is if mu equals 0. So the Wronskian is 0 if and only if mu equals 0. But in the case that mu does equal 0, the roots of the characteristic equation, gamma plus I mu, are not actually complex. They would just be a real value, gamma. So finally, we can conclude that if r equals gamma plus I mu is a complex solution to the characteristic equation, then y equals c1 e to the gamma t times cosine mu t plus c2 e to the gamma t times sine mu t is the general solution to the differential equation ay double prime plus by prime plus cy equals 0. So we now know how to find the general solution to any second order differential equation of the form ay double prime plus by prime plus cy equals 0, where the characteristic equation has either complex roots or distinct real roots.